All right. Next, we have Amir Shaikhha on restaging domain-specific languages. Yes, please go ahead.
Yeah, thanks for the introduction. This is Amir from the University of Edinburgh, and perhaps the site title is a better representative of what the talk is going to be about. It's actually a flexible design pattern for rapid development of optimizing compilers. Let's start with the motivation. So this session is about optimizations, I believe. So we are interested in building compilers. And actually from the previous talk, you realized how difficult it is to build a compiler. So even just the inlining of a compiler is very difficult. So now you can imagine building the entire compiler, how difficult it's going to be. So in practice, if you see, as opposed to the GHC, which is written very nicely in a high-level language, most of the compilers out there are written in low-level languages, C, C++, Rust. And they have a steep learning curve, meaning that if somebody wants to contribute in extending that compiler, it's going to be difficult. And there are some compiler frameworks out there that they try to make it easier. Whether they succeeded or not, that's a different story. So for example, the MLIR framework is basically one of the industrial quality compilers out there that is being extensively used to build basically optimizing compilers for domain-specific languages in Google or some other companies. However, if you talk to functional programmers, they would say that you have to use a functional language to build a compiler. Basically, some of them, I don't know who is the originator of this code, but at least I know my colleague Philip Wadler has said that several times, that basically functional languages are like domain-specific languages for building domain-specific languages. And why is this the case? They provide very cool set of features. So they have algebraic data types, which are basically the natural paradigms to define language, domain-specific language or language constructs. They have pattern matching, which makes it very easy to rewrite rules or analysis over the different constructs of the language. And also, if you recall from the previous session, they are also very good to embed languages inside them, because some of them have very powerful type systems that are going to simplify some part of the front end of the compiler. But here I'm going to focus mostly on the back end and middle end of the compiler. Let me give you one example, and throughout this talk I'm going to use the newest version of the Scala programming language to basically show you how we can build a compiler. So this is basically the fsmooth language, a domain-specific language for array programming. And on the left side, you can see the grammar of this language. And on the right-hand side, you can see how we define the ADT for this language. So there are enum types, which are basically a new feature added in Scala 3, which makes it very simple to build algebraic data types. You can see that for every construct in that language, we basically have one case in the right-hand side. So for example, we have build, length, getting an element of the array. So build basically constructs an array with a given size and with the provided function. Length basically gives you back the size of the array, the number of elements in the array. The get is basically looking up the element at a particular index. Addition and multiplication is kind of obvious. The constant values, variable, and defining basically variables. Let me give you one particular example. This is how we can do the Hadamard product between two vectors. So we have vectors v1, v2. They're basically arrays. We are building an array with the same length as one of the vectors. And for element I of the result vector, we are multiplying the element I from the two input vectors. So this is basically the concrete syntax of a particular program. This is how it's going to be represented in Scala by using the ADTs. you can see that at the top level, we have basically the build node. The first parameter of the build node is basically a length of a given symbol. Then the next one is basically the input to the lambda. And then we have a multiplication of getting the particular element. So this was the first side of the stuff, which was how we can define a program, represent a program, and define a language inside Scala. But I promised to build a compiler, which means that we want to write a transformation now there. This is how we build basically a partial evaluator for a program in Scala. So you can see that we have a function called PE-rec, which stands for partial evaluation in a recursive way. And you can see that we have used pattern matching. It's very cool, yeah? Except there is some part of the program that I didn't show you. That is ugly. It's beautiful, but it is boilerplatey, yeah? So what does that mean? It means that if I need to define L different languages, and each of them in average have N different constructs, and for each of the languages, I want to define T transformations. This is basically the amount of effort in terms of lines of code or whatever, a constant factor of that. I would need to basically develop the compiler for that language. So is there any way to basically simplify that? So you can see that, for example, one of the nice work is actually the strategic rewrite rules or transformation strategies. So for example, I defined once a way to basically, in a bottom-up manner, apply a bunch of rewrite rules. So I do this kind of ugly thing only once, and then whenever I want to implement the partial evaluator, I can just write the interesting cases for that. So what am I doing in the partial evaluation? So basically, I see whenever I have an addition, if I see the two inputs are constant, then I want to fold them. Or whenever I have a multiplication, whenever I see the two inputs are constant, basically, I want to, again, fold them. The rest of the cases are basically the boilerplate things that are involving, like, okay, doing a bottom-up transformation and recursively applying the same optimization. So the good thing is that now we have no boilerplate. But the issue is that, okay, we have done the bottom-up transformation strategy. In some cases, I need to do it top-down or some other more sophisticated styles of applying the rewrite rules. And also, while I'm designing the language, suddenly I realize that, okay, I need to extend it slightly. So then if I have language extensions, I have to go through all the transformation strategies that we have developed and extend them with the new set of language extensions, which makes us again a bit unhappy. But it is quite a lot of achievement in comparison with the first style that we have seen. So if we have, again, n different constructs, and basically we have the lowercase t, which is significantly less than the capital T base transformations, like top-down, bottom-up, then I need to just, for the capital T transformations that I'm interested in, I need to only apply it into the actually affected constructs. I don't need to apply them in all different language constructs. So what I'm going to show in the paper, and you can refer to the paper for more details, is basically a design pattern to improve even over that and make it easier for compiler developers to build their next compiler. So the design pattern that I'm proposing actually uses a feature in functional languages called type classes. It basically introduces a type class interface, which are basically some mechanism in functional languages for somehow simulating what inheritance would do in object-oriented languages. And this type class interface is providing just two operations. One operation is for each language construct is going to give back the set of its children. And the other construct is going to basically reconstruct that construct with a new set of children that I provide for it. So if I want to show you the code, this is how the interface is going to look like. You can see that I have basically two operations. One is giving me the set of the children. So for a given expression of type T, it's going to give back the list or the sequence of its children. And the other one, for a given expression that I pass to it, is going to return a function that if I supply it a list of new children, it's going to reconstruct that, that expression. So with this simple interface, this is how I can implement a bottom-up transformer. You have seen in the previous slide how many lines of code I had to do. So now you can see it's just, how many? 5 lines of code. That's great. Not only that, this is actually the top-down transformer. This is also 5 lines of code. Here, though, I'm using some advanced features of the Scala programming language. If you see, I'm doing a pattern matching over the Restage type interface. That looks a bit weird. I'm kind of using a feature from the language called the extractor feature. What is the extractor feature? It basically allows you to extend the pattern matching inside the language. How does it do that? So think of the case whenever you're building a construct, you're constructing an expression. Basically, it's like applying it to the set of its children. And somehow the extractor is doing the reverse of that. And that's how it is called in the Scala. So it's called an unapply. So it basically gives you a way to do the pattern matching over that. So basically, whenever it sees the following pattern matching, it's going to, the Scala compiler is going to desugar it into the following unapply call. So we extend basically the pattern matching over this Restage type interface. I'm using even more advanced features here. If you see, there are these kind of type parameters which I'm basically saying, putting something in front of them. These are known as the context parameters, which are basically somehow, for the Haskell programmers, these are basically a way to specify basically the type class, the functions that have type class inputs as constraints inside them. And okay, there is no free lunch. Of course, at some point of time, I should have the boilerplate code. Where is that? It's actually to provide that type class interface. We have, again, boilerplate code. But the good thing is that I need to do it only once for every language. Actually, twice, because I have to do it once for the children and once for the kind of recreation of each of the constructs. Again, we have boilerplates. And if you want to extend the language again with some additional constructs, again, we have to extend each of these 2 cases and be careful that we are actually extending it. But the cool thing is that now we have improved the productivity slightly more. Can we do better than that? So it's the GPCE conference. There should be something generative happening here. And this is what we are doing. We are basically using metaprogramming. And there is a new feature in Scala 3 called the type class derivation, which actually gives a systematic approach to basically generate the type class instances and automatically generate the boilerplate code that I've shown you before. So you can either use Scala macros and reflection. The difference between them is that one of them is actually doing the generation in runtime, and the other one is actually doing the generation in the compilation time. So the interface that we have to provide is basically this one. You can see that I have annotated also this particular method, which is called derived, which is actually for type class derivation within line. I'm not going to show you the implementation. You can refer to the paper to see the, actually it's in the appendix of the paper because it's a bit long. But the good thing here is that we just do it once across all languages. And by we, I mean poor me. You don't need to do that anymore. So then for the next language that you want to define, you're just going to put this thing, these two words in front of it. And believe me, it's going to have no boilerplate. And if you want to extend the language, just add another case here and say, what is the new language construct? And it's going to make the extension of the compiler for new language constructs also very easy. And as a result, we have basically improved even this one further. So what does that mean? If you have L languages and you need to define T transformations, which actually effectively these transformations are going to touch like small n, which could be like 1 or 2 constructs. This is the amount of coding that you need to do. So compare it with this case that for all transformations, you had to consider all pattern matching cases for all language constructs, even if they were kind of irrelevant. Just to do the recursive application of them, we needed to provide them. But one might wonder that, okay, you did the generation of that boilerplate code. How about the performance? Does it have any impact on the performance of compiler? What does that mean? It means on the compilation time. You're building a compiler. So is it making the time that it takes for the compiler to do its job less or not? And basically here we have several cases that we are considering. Of course, whenever you use the restage interface, it's going to have some overhead. Because whenever you're defining it recursively, there is kind of no abstraction that you're using. You're actually touching the nodes directly. So there is some slight overhead, but if you consider the case of using the restage interface, where we were developing the type class instance by our own with the boilerplate code, in comparison with the case that we use macros to automatically generate that, there is no overhead. If you use reflection, of course, you're doing the generation of that boilerplate thing in the runtime, there is going to be a huge overhead. So the takeaway message here is that don't use reflection, use macros. And you would have negligible overhead. So in the paper, we are going to basically show that the design pattern that we propose is basically compatible with one of the design patterns that is used heavily for imperative compilers, which is basically the visitor design pattern. And also, it nicely aligns with strategic rewrite frameworks. So this Stratego framework or its implementation inside Scala, which is basic, one of them is the Elevate framework. And also, you can not only develop transformation passes, you can also develop analysis passes with that. And we show somehow some ideas how this idea can be implemented in other functional languages, such as OCaml and Haskell. And we definitely show more examples, and the implementation of the type class derivation that I didn't show here is also in the paper. So this has been already used in some of the compilers that we developed over the previous years. So I didn't come up with design pattern just now. I had that since 2019. So we have used it basically to implement an automatic differentiation framework on top of the F-smooth language that I've shown you, which was presented in ICFP 19. We have used it also for a domain-specific language that we have used for end-to-end data science for hybrid workloads where you have database-ish workload and linear algebra-ish workload. That has appeared in Uppsala 2 years ago, and also CGO this year, which was in Edinburgh. And we have also used it for another domain-specific language for basically probabilistic programming. To summarize, I've shown you the Restage design pattern, which basically gives a flexible and agile compiler development paradigm. It makes the compiler more concise, less error-prone, and also we have seen that, okay, at some point of time, we have to write some boilerplate code. I've shown you how we can use metaprogramming features basically to reduce this boilerplate. And one nice thing with that is that it has no dependency whatsoever on any other framework except the implementation that, of course, I gave here. So that means that you can basically use this design pattern easily to build your own compiler. Perhaps if you have built a lot of compilers, you realize that, yeah, maybe you already had that design pattern. I was just lucky to publish it sooner than you. And we have successfully also used it for building several DSL compilers, and I have shown you some of the examples before. And with that, thank you for your attention.
Thank you for the talk.
Yeah.
I was wondering, looking at your derived functions for getting the children, I saw a capital T in there, and I was thinking, okay, so this works for your example, which is an expression language, where it is an expression and the children are expressions. What if my language has both statements and expressions?
Yes, so that's a very good question. It could be the case that you have a more sophisticated DSL that basically the grammar has like expressions, and then it has like terms, and then it has like term two, it has like clauses and these kind of things. So then it would be slightly more complicated than that. So I would say that, for example, in that case, you either should have like one common kind of interface for all of them, and then, of course, you can reuse these. So, for example, even if you have like terms, expressions, you can have like expression or term as the kind of upper trait for them, upper interface for them, and then reuse the same pattern. Or alternatively, what you can do is that rather than just returning one sequence, you return a pair of sequences or a tuple of sequences. And that makes also the rebuilding slightly more complicated than that.
So the suggestion that you have there, does that mean that I have to be like you and I have to actually be sad and implement this?
Yes, unfortunately.
Okay.
But the good news is that if we see more patterns of the cases that happens there, perhaps we can have a kind of boilerplate, this metaprogramming thing for that more general case. I think that it should be possible to basically slightly generalize the macro framework to basically handle those cases as well. Yeah, but right now, no. We have to be sad.
Thank you.
Yeah.
Thank you. That sounds like a design pattern I would like to use.
Yeah.
But so there's some questions I have before I can do that. So one thing connects to Jeff's question. So what if I have statement and expressions and they're mutually recursive? Because then it looks to me I would need one type class instance for expression, one mean, one restage instance for expressions and one for statements, and now they cannot be mutually recursive.
Yeah, so actually the solution that I would suggest for that is that you have to slightly...
You have to couple them somehow?
Yeah, either you can couple them, or if you want to have them decoupled, you have to basically change the interface so that rather than just having this interface that has just T, it has basically T1 and T2, let's say.
T3 and T4 and T4.
And T3 and T4. So basically you have to define a heterogeneous list then for that, for the kind of more general case of that. If you want all these kind of nice nice catches by the compiler. But I think if you couple them together, then you wouldn't have that issue.
So the other limiting factor I wonder about is, so you talk about, in the end of the talk, you had like the slide where you show enum exp and then derives restage and then everything's green, happy faces. So, and you say that now it's extensible, right? So I can add more cases to that data type.
Yeah.
Well, what if I actually need an open data type?
Oh,
Right? This is, so just to explain, right? So this is a closed data type in the sense of it's defined at one place and you cannot add cases in another file. But
Yeah.
I want that kind of extensibility. So I would rather have this be a trade with a couple of cases and then add more cases elsewhere.
yeah, that's a very good question. Let me tell you a dirty secret. I do have that case in all these different languages.
Yeah.
So I have a construct in the language called external function, which basically has a kind of name and a list of parameters. And so basically as the input, it has basically a sequence of expressions. And basically this design pattern allows you basically to, for those cases, to have a kind of override the kind of default implementation that you would have. So still, for that external function, you would say that, okay, how the rebuild and the kind of accessing the children would work. And I think, yeah, if you're extending it in whatever, that behavior doesn't change.
I think we probably should take the rest of this discussion.
Yeah,
offline.
sure.
But I think, I mean, I really like that this kind of paper where we share about design patterns we found while developing compiler. I think this is very valuable, very interesting.
Yeah, thank you very much.
Another question? Yep.
On the graph where you're comparing the execution time against the size of the program, what was the unit of measurement for the axis of the program size? How did you measure the program size?
Oh, yeah. So I basically, so this is actually for the inlining optimization. And so here the program size is actually the number of terms that are involved there. So I had basically, so in the paper we are exactly showing what is the program that we are kind of, it's a synthetic thing. So we are just increasing the size of the program. And yeah, here the unit is basically time, the compilation time.
Thank you.
Yeah, sure.
I was just curious why the unapply was a partial function. It returns some, an optional value.
So let me bring that up again. So why unapply was what?
Was a partial function, right? It returns some.
Yeah. So here the general kind of interface for unapply is that it takes an expression and it returns an option of basically something. And whenever, so here I said that it's sum, it means that whenever I apply it, it should match. It should return something. And it is basically for this case because I know that there is no other case involved. Whenever it's of type T and that type T follows the constraint of the restage type class, then it should match, definitely. That's why here the return is actually has type sum. But in general, in Scala, basically, it should have an option type, which could be either none or sum. If it returns a sum, it means that the match was successful. If it returns a none, it means that the match failed. So it then, in the pattern matching, it should go to the next case. Yeah. And I believe that the Haskell language also has an extension for that. I don't, perhaps Lionel knows. So I know that in F#, it's called active binders.
Active patterns, right?
Or active patterns, yeah. And yeah, in Haskell there was something like a view, perhaps?
Pattern synonyms and views.
Yeah. It's basically the same thing to basically extend the pattern matching.
Okay. I think, Amir, that your history of this pattern is a bit incomplete.
Yeah?
I remember seeing it when we were working in the systems compiler circa 10 years ago. You were already using it. I remember it.
Maybe.
So it's even older than you remember. I remember that one of the things that I found a bit unsatisfying about it is that it's a bit error prone, in a sense, right? If you pass a number of children that's not the same number as what you got, you get into problems, right? It's easy to pass the wrong list of children to rebuild the node, right?
Oh, that is partially correct, because it could be the case that, so in the current, that's a very good point. So let me basically explain it more, what is meant here. So basically here, you can see this rebuild thing, which basically I do the pattern matching. And then here I pass the set of the children to it and say that, okay, for this new set of children, rebuild it. So what Lionel is saying is that I don't need to have further checks to see whether the number of children that I passed is actually correct or not. What happens if I basically pass 3 children in this case? So I need 2 children. What if I pass 3 children? What if I pass 1 child? So then it's going to be a very kind of ugly exception. Whereas if you basically were writing the pattern matching in this way, there was a nice compilation error that was provided. So basically, here I do agree with you. With the macro thing, then you can inject those additional checks with the right error message.
Yeah.
The issue though is that it's going to be one-time error messages, which could be a bit ugly. But on the other hand, we're reading a compiler. The runtime of the compiler is actually the compile time. So it should be okay.
Right. So I had a second question, actually. In this example, expression language you give, you have this sim case, which is also used as the name of the binding in the let binding. The type of the name in the let binding case is also sim.
Yeah.
So, but that one is not passed as one of the children.
Yeah.
Is that on purpose?
Yes. Yes, because and that quite happens. That happens often whenever you are. Yeah, perhaps I have to show here. So the first parameter here is not an expression; it's a symbol. And the assumption that we make here is that we don't want to rebuild that, or
right,
we don't want that child.
What if you're doing some renaming or something and you actually wanted to rebuild this one?
Oh, you don't need that. So we have actually examples in the paper that we are basically doing variable substitution. And usually what you do there is that you have some sort of additional context there that you're passing around that information. But you don't need to basically do the transformation there. Or if you need to do something sophisticated with that, then you are not following it to the default case. You're handling that in your kind of pattern. So it precedes the restage matching case.
Yeah, so you have to handle all the binding forms then. So that's another constant factor.
Yes.
Account.
The binding forms are a beast.
Okay, cool. Thanks. Yeah, if there's no other question, it's thanks Amir again.